Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper from the Hugging Face trending list, published on August 26, 2025, just yesterday. The standout result is that this paper matches 8 expert mixture of experts' performance with far lower memory access, while delivering gains on memory-heavy tasks like plus 1.6 on long context memorization, plus 6.2 on multi-round memorization, and plus 7.9 on in-context learning. The paper is titled UltraMemV2, Memory Networks Scaling to 120B Parameters with Superior Long Context Learning. And, as we will see later, the implications for efficient sparse computation are significant. In short, the redesign integrates memory into every transformer block and shows activation density matters more than total sparse parameters. Also, the authors shared an official GitHub repo. You will find the UltraMemV2 implementation with training and inference code, configs, fused ops, Docker setup, evaluation scripts, and example launch scripts. The README outlines installation via OLMOE, dataset preparation, and a full training command. Checkpoints, tests, and docs are included. Alright, the introduction just set the stakes around matching 8 expert mixture of experts with far fewer memory reads. Figure 1 compares 3 sparse layers side by side, which helps clarify how computation and memory access differ. The MOE panel routes a hidden state through a gate to pick experts, combine pre-values and values, and produce outputs. The PKM panel factorizes keys into row and column sets, scores with a query linear layer, then retrieves values via product quantization. The UltraMemV2 panel adds Tucker-decomposed query key retrieval and explicit pre-value and value projections, so the model activates compact value paths with top-M selection while keeping memory traffic low. So, Figure Table 1 compared models across training stages and benchmarks, and the pattern is clear. Table 1 shows that after continued training, UltraMemV2 with 60B sparse and top 768 matches or surpasses 8 expert mixture of experts on open bench and hard bench, which supports the claim about activation density. The rows also indicate that the 120B sparse top 256 variant lags slightly, so denser activation helps despite higher latency. The training loss and eval loss columns confirm steady gains with longer training. So Table 2 focuses on long context evaluations and highlights where the memory layers shine. The table reports clear gains for UltraMemV2 over SeedMOE on long context memorizing, multi-round memorizing, and in-context learning, which matter because they stress persistent recall. Fine needle also ticks up slightly, while key value retrieval jumps strongly. Multi-hop reasoning drops, so the average still improves, but with that trade-off noted. Okay, the last table showed strong long context gains. Figure 2 now compares pure value processing to a baseline with value embeddings, holding memory access and compute fixed. The left panel shows slightly lower training loss for PEER, ending about 0.02 lower, which signals more efficient learning. The right panel shows higher open bench accuracy across training, with about 3 points improvement at over 300 billion tokens. The benefit comes from replacing stored value embeddings with a compact feed-forward network that processes the retrieved values. Wrapping up, 2 takeaways stand out. Integrating a memory layer into every transformer block, plus PEER-style value processing, lets sparse memory networks match 8 expert mixture of experts while cutting memory access, and higher activation density beats sheer sparse parameter count. The broader implication is cheaper, long context capability at scale. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.